All right, welcome everybody to this collaboration-wide paper review presentation. We're very lucky to have Matt Price from UCL. He's going to give us a talk about these three papers that have been in internal review for the last few weeks. Matt's a second-year grad student at UCL working with Jason McEwen, who you can see there on the side of his video. And without further ado, I'll turn it over to you, Matt. Thanks very much.
Hi, so this is going to be a hopefully quite fast and not too long review of the three papers that have just gone through desk review, focused primarily on formulating the mass mapping, so the convergence reconstruction problem as a hierarchical Bayesian inference problem. So the three main sections, I suppose, are defining what the problem is and how one might solve this problem, and then discussing the uncertainties in the reconstruction, and then general results from the three papers. But more detailed discussion will be in the actual papers if you're interested. So just to set up the problem, what is it that weak lensers actually observe? So there are two primary fields of interest at linear order, which are the shear and the convergence. So the shearing signal is essentially a perturbation to the ellipticity of observed galaxies, and the convergence signal is a magnification factor, essentially. Now the problem is, sometimes people are interested in calculating statistics on the convergence map, but because of the mass sheet degeneracy, we can't actually observe that. So typically people will make observations of the shearing field and invert them to get estimators for the convergence. So the two quantities, the convergence and the shear, are related to the underlying integrated line of sight mass distribution phi by these two relations 3 and 4, where these operators here are the spin raising and lowering operators. On the sphere, these spin operators are defined as such, and combining those two equations 3 and 4 and these operators 5 and 6, you can get a mapping from shear to convergence in spherical harmonic space, which is given by equation 7. Now, typically people are interested more in small patches of the sky. So to avoid working with computationally taxing spherical harmonic transforms, it's well approximated by Fourier transforms. So on the flat plane, the spin raising and lowering operators are given more simply by equation 8. Now, combining these with the relations between gamma and kappa, the convergence, we can get a relation 9, which is the forward model in Fourier space. So this is to say that if you were to have the Fourier coefficients of the shear field, you can relate them to the Fourier coefficients of the convergence field by this mapping D. Okay, so how does this help us? So you can set up mock observations, like the model through which you would actually observe shear fields. So given some underlying convergence field kappa and some additive noise n, which we take just for simplicity here to be IID Gaussian noise, then you get equation 11, which is just how you actually make observations of their shearing field and how that's related to some underlying convergence. So this operator here, phi, is what's typically called the measurement operator. And it's just, as we discussed before, the forward model of how you go from convergence to shear. So clearly, this isn't a completely representative model of how observations are made, because you have PSF corrections, you have photo Z errors, etc., etc. But in a hierarchical setting, you can simply fold all of these into the hierarchy quite easily. Particularly, you can just adjust your measurement operator phi, and that's the only change. So there are some few loose constraints that you must satisfy, but we'll discuss them in slightly more detail later. So given that we have this setup problem of how your noisy gamma shear observations are made, and how you can infer your convergence from that. Typically, people might say invert that relation, so take noisy shear measurements and just apply that the inverse of the forward model. The problem with that is that it doesn't account for the noise at all, and this inversion is ill-posed. So a natural way to deal with these kind of problems is to pose them as a Bayesian inference problem. So that's to say that the posterior, the probability of getting some convergence, given that you measured some shear, can be recast in terms of some likelihood and some prior, where the prior is some a priori knowledge that you, or supposed knowledge that you have of an underlying field. So fine, what's your convergence estimator? So in a Bayesian setting, I guess the best in terms of it maximizes the posterior odds solution is the one that maximizes the posterior. So because of the monotonicity of the logarithm function, that is the same as finding the solution kappa, which minimizes the negative log posterior, which is just what's given by equation 14. So how do we choose to set that up in this sense? So because we have assumed that it's Gaussian noise, just for the moment, you can change this, then our likelihood takes the form of a multivariate Gaussian. So specifically in this case, we've assumed that the noise in each pixel is the same. Well, it's drawn from the same Gaussian distribution, and the covariance is diagonal. And then you have to choose some prior. So in this sense, we've chosen a Laplace type prior, which is just promoting sparsity in a wavelet dictionary. Now, an interesting thing about this is that other reconstruction techniques that use Laplace type priors tend not to address this mu factor, which is a weighting for that prior. So in this framework, if you're going to treat it as a hierarchical problem, I mean, the typical thing that you do is you assign a hyperprior to that and you marginalize over, which is exactly what we've done here. We assigned a gamma type hyperprior, which we then marginalize over. Now, it's important to note.
So the prior is a prior on kappa or on all the systematics? So you use the same sort of prior shape for all of them?
Well, this prior is specifically on the wavelet coefficients. So this is to say that if you take your convergence, your reconstructed convergence map, you would expect that in a certain wavelet dictionary, it would be to a very good accuracy represented by a very small number of coefficients. And it's really weighting off to say that the noise is fairly uniformly distributed in the wavelet dictionary. So you can cut out the noise very efficiently. And that's what this prior is enforcing.
Okay, thank you.
Does that make sense? Sorry. So it's important to note, though, that all of the uncertainties, which we're going to discuss later, apply for different combinations of likelihood and prior. The only requirement is that your posterior has to be log concave, which that's satisfied by a very wide class of priors and likelihoods. So a discussion of whether or not a Laplace prior is the best for a certain situation, it doesn't matter. Like, all the uncertainties still follow. So with that prior and that likelihood, minimizing of the negative log posterior simply gives you this objective function. So like I just mentioned, if the posterior is log concave, then this objective function, which is, it's basically the argument, the exponents from your posterior, that forms a convex problem. So you can solve for your map solution very quickly using highly optimized convex optimization algorithms. So then the problem is, okay, you've posed the problem as a hierarchical inference problem, and you found the most the maximum a posteriori solution, so the one that maximizes the posterior odds, but you have no idea of what the uncertainties on those values are. So typically, one would solve this problem with MCMC sampling, and then you get an idea of what the posterior shape is around your solution. But that's extremely computationally taxing. So what you would recover if you were to do MCMC is a Bayesian credible region. So the Bayesian credible region is defined by some mass, some probability mass in your posterior space that it contains 1 minus alpha of the probability. The problem then is that you could choose a very large volume very far from your map solution and still have 1 minus alpha. So there are actually infinitely many of these different sets, C alpha, that you can choose. So the optimal one, in the sense of the smallest volume which will contain 1 minus alpha of your probability, is the HPT credible region. Okay, fine. To actually calculate the HPT credible region, you need to calculate this level set threshold, epsilon alpha. Now, epsilon alpha, to calculate that, you need to evaluate this very high dimensional integral. So when the dimension n of the convergence map is very large, this integral becomes completely intractable, or at the very least, very difficult to compute. But recent advances in the field of probability concentration theory and information theory, working on kind of the a priori knowledge that as you go to very, very high dimensions, so for a dimension n, where n is very big, almost all of the probability becomes concentrated on a very small subset of the n-1 shell. So when you work with this, and the proof is a bit complex, you end up getting to the point where you can define a conservative, so it will always be larger than the actual value, approximation epsilon alpha prime, which is given by equation 21. Now, the interesting thing is, given that you've already solved for your map solution, to get the epsilon alpha to define an approximate HPT credible set is just an additive constant, this Tor alpha root n plus n. So you can recover a fairly good estimate of what your level set is almost instantaneously. Now, a caveat is these types of approximate HPT regions are at the cutting edge of research in information theory. But this framework, as you can pick and choose whatever prior and likelihood you like, provided that the posterior is log concave, you can also update this HPT credible, approximate HPT credible set as and if and when new approximations are derived. So you can update this to stay in line with the most recent theoretical predictions. Not predictions, theoretical bands. So then how do you actually use this idea of a level set? So one way you can, which is the way that was presented in paper 1, along with in the radio interferometry setting by Kai et al. In 2017, is the idea of hypothesis testing. It's not a particularly new idea, but it's a new application of this idea. So given that you reconstruct some maximum a posteriori convergence map, so you reconstruct a convergence map, you want to tell whether or not some feature inside of that map was physical, so necessarily must be in that map, or is inconclusive, okay? So the idea is you recover your map, you locate the feature, you remove said feature, and then you calculate the objective function again. So this f of kappa, g of kappa. Sorry,
so that's a question, yeah. So this is a very basic question. So normally if you were to create a credible region, it would tell you sort of what the value of kappa was, right? And the maximum would be, the maximum of your likelihood would be the maximum value of kappa, and then there would be some sort of, say, you can think of it as an error. But what you have here is sort of a spatial map, right? And so what I'm curious about is, at every point on the spatial map, are you using the maximum value of kappa that you found in your credible region? Or I'm sort of unclear on how the error on the credible region of the value maps over to the spatial coordinates.
Sure. So, every single pixel in your reconstructed map is a dimension. And the map solution is the one that maximizes the posterior over all of those different dimensions. So so it locally maximizes the posterior every single position.
Oh, I see. So it's not done. It's not done pixel by pixel. Okay, I understand. So somehow, as you moved off the maximum of the posterior, the entire map over the spatial dimensions would change. Is that right?
Yeah, maybe I can also just
Sure.
add that basically this is just defined implicitly. All we know at this point is the value of that level set defining that, higher dimensional region. And then now there's a variety of ways that you can use that to recover. So you can do some of the things like you mentioned, find error bounds at the pixel level. And that's something that Matt's probably going to come on to in a minute in some of these other papers.
It's on the next slide.
Okay, thanks. That
basically,
Thank you.
at the first stage, it's all implicit. And then you have to think about, well, how do you use that in practice? And there's actually quite a variety of ways of doing that. So maybe... hopefully, maybe when Matt starts talking about one of the other papers, he might answer your question, but if not, let us know and we can discuss some more.
Okay, thank you.
Okay. So basically, what you're doing here is you remove some structure and you create a new convergence solution. And you're asking, is this solution rejected by the data? So if the objective function of this new surrogate solution is above the level set threshold, then this solution did not belong to the credible set. Which therefore means that, therefore implies that the feature that you removed was necessarily required by the data. So it's a physical feature at some confidence level alpha, which defines the level set. Kind of conversely, if you remove that object, calculate the objective, and it's still within the credible set, then you cannot determine whether or not this was or was not physical. So that's not to say that it's not physical, it's just that it's inconclusive. So a second form of uncertainty quantification is local credible regions, or local credible intervals, rather. So the idea here is that you recover your convergence map, and then you iteratively go through every single pixel, so every single dimension inside of your reconstructed posterior, and you iteratively raise the intensity within that pixel until the overall solution is no longer within the credible set. So once you find this maximum value, that is the maximum value that that pixel could have taken at some confidence level alpha. And conversely, you can move it down and you'll find a bound an upper and lower bound. So a range of values that would be accepted, would not be rejected by the data at some confidence alpha. And you can do this for every pixel in your map, or you can do it for combinations of pixels, so larger superpixel regions. And this is to say that you end up with a map of your recovered uncertainties at the pixel level. So the third...
Sorry. Doesn't this procedure give you the posterior PDF for pixel value I, given that all the other pixel values are fixed at the maximum posterior value? So it's a conditional, not a marginal PDF.
Well, yes, and also... But that's what you want, right? Because all the other pixels in their map solution minimize the objective function. So when you just focus on a single pixel and move it as high as possible, that is the highest that it will ever get to. If there are any changes at all in any of the other pixels, that's going to make it so that you can't move this pixel as far as you can normally. Does that make sense?
So you're saying it's a conservative uncertainty?
Yeah, well, it's basically the absolute largest that it could possibly be.
Okay, thank you.
It's extremely conservative.
Yeah, so then the question is, okay, fine, you could say, I accept any value, right? And have it be infinite. But the point is the approximate level set actually has a derived upper bound on its error. So it will, that's also in the papers, which I would recommend you read, but it says that the error introduced by the approximation will at no point be larger than a certain value. So you can't just, like you're going to mention, have infinite error.
No, what I'm saying is, even if your epsilon prime were exact, to look at the bounds of the joint region instead of the marginal is very conservative.
Sure.
Yep. I guess the background is, I mean, the motivation here is, if you could do MC-MC sampling and recover the full posterior distribution, then you would. But we want to consider settings where that's not going to be feasible. And that's typically not feasible because the dimensionality is just too high, but also because we're considering these sparse priors, which typically work very well in practice, but also not differentiable. So it's difficult to apply kind of standard MCMC methods where you often exploit gradient information, which you don't have in this setting. If you're really pushing to very high resolutions, then again, it's difficult to do. So the motivation here is more, let's do something that we can scale to very, very large data sets, and typically using optimization methods rather than MCMC methods. But of course, we still want to do uncertainty quantification, but we don't have access to the full posterior. So we do basically what we can to recover approximate uncertainties. And given these uncertainties are approximate, we want to make sure that they're conservative, so we're not underestimating. So just a bit of background for kind of like where we're coming from. Yeah.
So it's a little bit in the spirit of variational Bayes, but you're doing some different type of.
Yeah, a little bit, yeah.
Okay. Any more questions on that? Okay. So then a third form of uncertainty quantification that you might want to do is finding the locational uncertainty of some reconstructed feature. So let's say you reconstructed some convergence map and you have some peak. And you want to know, okay, where could this peak have been located? So it's fairly straightforward. What you would do is you remove that peak from the map. Obviously, you have to make sure that you remove it in the correct way, but the details in the paper. You remove that peak, and then you iteratively reinsert this peak at different positions. So, I mean, you might kind of nested sample this peak out until you get to a situation where the solutions that you're generating are no longer in the credible set. And at that point, you end up mapping out pixels that are not rejected for the location. I guess this the location of the center of that feature. You can then form the convex hull of these features, and that will give you the locational uncertainty. So a location isocontour on your convergence map of where that feature could have been located. So I guess the fourth and final uncertainty quantification is more in the spirit of a global statistic rather than looking at individual features. So something that people typically will compute from a convergence map, you can do it in shear as well, but is the peak statistic. So this is essentially, you have a reconstructed convergence map, you cut at some intensity, and you have the subset of the pixels that are above this intensity. And then within that subset, you then further calculate the number of peaks. So the number of peaks would be defined typically as the number of pixels that are larger than their 8 surrounding pixels. There are some other definitions, but that's the one that we've gone with for this illustrative case, I suppose. So then the idea is, how do you actually leverage these uncertainties to uncertainties on the aggregate statistic? So the idea is that you recover your convergence map, and at a given intensity, you have a certain number of peaks, and that's your map solution number of peaks. You then iteratively remove the peaks at each time, recalculating the objective function until the solution is rejected by the data. And at that point, you now have a solution with the fewest number of peaks possible, which gives you your lower bound on the peak statistic. And then you can invert that problem and calculate an upper bound, which is on the right-hand side. It's a very similar process. So in the first paper, just some illustrative examples. These are Bolshoi n-body simulations. And we perform the reconstruction, and these are a set of hypothesis tests. So this first red box in the upper left image is just asking the question, is the central peak physical or is it a physical peak or not? And we remove it. The objective function soars far above the credible set threshold. And then the conclusion is that feature was physical. And then, okay, that's quite obvious. It's a really big feature in the reconstructed map. What about a smaller feature? So the blue box in the top left image is a smaller subhalo of the main halo. We remove that and ask the question, was that physical? If I remember correctly, that one was determined physical as well. And it's smaller. But just an example of where this case is, I guess, not able to say anything conclusive is this green box, where it's a very, very small, far out subhalo. You remove that, and the objective function doesn't rise by enough. So the conclusion in that case is that the is that the data is inconclusive to tell whether or not this feature was or was not there. So it's not to say that it's not physical, it's just not conclusive. So it's not actually only, like a hypothesis test doesn't have to be pixel level structures you're removing. You could also remove like blur structures into one. So for instance, on this lower plot, we have two very close peaks, and we're asking a series of questions to try and determine whether or not that's two peaks or one peak. So in the most naive case, which is test one, is we remove one of the peaks, and that was that was determined to be physical. So that implies that at the very least, that peak of the two was physical. You might then ask, okay, let's blur these two peaks into one, just with some very small blurring kernel, and then ask the question. So test 2 and test 3 both do that, and in both cases, the solution is no longer accepted, so it's rejected, which implies that these two peaks are actually individual peaks and not just one combined. So again, we do similar tests on a third Bolshoi cluster, and then we also do tests on some buzzard simulation data. So these follow in exactly the same way. You observe some feature, you remove it, and you ask, is that physical or is that not? So this very large, I guess, triple peak here in the lower left image was determined physical. The smaller peak in the bottom left of the bottom left image was determined physical. And the small void, which you can see was test 2, was not determined physical, but that's mainly due to the intensity of the voids, which is significantly lower than the intensity of peaks. As a final thing for the first paper, we applied the technique to the A520 merging cluster. So we got these reconstructions. They agree well enough with other reconstructions. We tried to determine using these tests whether or not these two peaks were physical. So we determined that jointly they're physical, but these data sets are too noisy that in this particular setting, you can't determine the physicality of any of these local structures. Certainly not this small intermediary peak that was the discussion of the papers in Chloe et al. 2012 and G et al. 2014. So in the second paper, we were primarily concerned with comparing the recovered uncertainties through these fast map approximations to a full MCMC algorithm. So because we're working with a class prior that's non-differentiable, we had to use a bespoke MCMC algorithm. The PXML algorithm, which I'm going to skip over for time purposes, was it's essentially an MCMC algorithm that supports non-differentiable priors. So what you'll see here is an input simulation map. So this is an n-body simulation, another Bolshoi map. You have on the top row the proper MCMC reconstructed uncertainties, local credible intervals, as I discussed earlier. And on the bottom, you have our map uncertainties. And you can see that kind of topologically, these are agreeing quite well, but they're also quite close. So like you were saying, these might be really conservative errors. They're not that conservative. In fact, we actually find that the uncertainties have a root mean squared error of 25 to 30%, but this is in both dimensions, so it's the upper band and lower. So that's roughly equivalent to 15%, 10 to 15% error on the recovered uncertainties, at least in this case, though it should be the same for, well, very similar for other cases. So again, you see a very similar match, and then we applied it to buzzard maps as well, just for variety. And the same again, they match very well. Now it's worth noting that we also did this to compare timing, so benchmark timing. So the whole point of this algorithm is that it can give you conservative, fairly tight approximate bounds on your posterior, but it's very fast. Could you say, when you say that the uncertainties have an RMS error of 15%, is that the size of the interval or the probability content? Like So how we calculated that is you take this, like the true map, and you calculate what the average root mean squared error is between that uncertainty map and our recovered uncertainty map. The details are in the paper if you want some more it's basically a measure of how close these two maps are. We also included the Pearson correlation coefficient. So we're also analyzing kind of how topologically similar these two maps are, so that the actual structures that you can see agree very well. So the correlation coefficient was, in most cases, above 0.9, sometimes getting as high as 0.97, I think, but don't quote me on that. But anyway,
sorry, Matt. I have a reviewer style comment.
Sure.
I think in this slide, if you want to compare these two error maps and make a statement about how conservative one error estimate is relative to the other,
sure,
it might be good to plot them with the same color bar.
So that's something that was raised, and that's fine. Just for visual purposes, though, if you consider plotting these on the same color bar, and it's something we considered, the range is roughly the same, but they're shifted, if that makes sense.
Yeah.
So you would end up with one of your map primarily being really dark colors and one of them being light, and that's just because it's a conservative approximation. So it wouldn't highlight that they're actually structurally similar, which is why we've chosen this.
Okay, thank you.
Sorry, I mean, the full details are in the paper, so the numbers are more important. This is just a visual representation. Anyway, just for time, I should speed up. The final thing that we did for this comparison was we did the timing benchmarks, like I was saying. And we found that the map solution, the map uncertainties, we can calculate roughly 1 million times faster, which means that in more complicated settings, so for instance, if you were to recover these kind of uncertainties on the sphere, where instead of doing Fourier transforms every position in your parameter space, you're just having to do, instead of Fourier, you're doing spherical harmonic transforms. MCMC algorithms are probably not going to work too well, but we can compute these fairly quickly. Anyway, the third paper is where we introduce these locational uncertainties and the aggregate statistic uncertainties. So here we have, again, some illustrative examples on some Bolshoi simulations. So you have, going from left to right, the first column is the peak that we're recovering, well, the image that we're recovering essentially. And then you have, in the actual image is the recovered solution for each of the noise levels. So you can see that you lose substructure as you go to more and more noisy situations. But then also overlaid are the 99% confidence isocontours of the peak locations. So you can see that as you go to noisier data, the locational isocontours get larger, which is what you would expect. Finally, the peak statistic. So the black line in the middle, so the left-hand side here is the log scale plot and the right is just linear. It's just log linear plotting, which is standard for this. The central black line is a maximum a posteriori solution for the number of peaks at a given threshold. And the red shaded region is the 68% confidence. So that's roughly 1 sigma. And the outer region, so the purple region, is your 99% confidence, which is roughly 3 sigma. So as you can see, it's quite constraining, but this is a very low noise, idealized, an illustrative example. But we also did it with slightly more realistic noise levels, though still somewhat optimistic. And you can see, as you would expect, all that happens is the error bars grow. So the blue shaded region here is just shading the region at which there could, at 99% confidence, be no peaks observed. So we have yet to use these uncertainties to actually get cosmological inference, but this is just demonstrating that you can leverage these fast fast Bayesian inference techniques to get these types of global statistics. So just to summarize, we've presented a highly generalized, fast Bayesian inference mass mapping technique on the flat sky, though there's no reason you can't extend this to the spherical sky. We've demonstrated a variety of principled uncertainty quantification techniques, and we've validated these uncertainties against MCMC. Sorry, that ran over a little.
No, that's great. Thanks, Matt. We really nice talk, and we have plenty of time for more questions. So let's see. Anyone have any things that you'd like to ask, Matt?
So this is Tom Laredo again. you couldn't try something like the Laplace approximation because of the prior? Is that what's going on?
So I guess the Laplace approximation's essentially based on Gaussianity as well, where you're basically
posterior Gaussianity. Yeah,
exactly. So basically, another one of our main motivations is we don't want to make assumptions of Gaussianity either kind of on the map or in for these distributions. So we want to kind of try and avoid that. I mean, one could do that if for sure. But I guess particularly for the cosmic share setting where we're looking at these mass maps, which are clearly non-Gaussian, we really wanted to move away from Gaussian assumptions in the prior, but also just generally.
Sure. So, but as a caveat, that's not to say that you couldn't use Gaussian priors. You certainly can.
Yeah.
But
yeah.
I actually wondered the same thing as Tom. That, I mean, when you do your MCMC tests, do you see in the posterior departures from Gaussianity?
Yeah, I guess we never looked specifically at that, but it's something we could look into. Yeah, for that posterior. I guess the thing is though, for those, yeah, I mean, still I mean, for the comparisons, I think that would make sense. But at the end of the day, you know, we're trying to aim for settings where we won't be able to do MCMC.
Yeah. So the MCMC setting was a 256 by 256 pixel image, which is low resolution. And even then it took a million times longer than us. And it took, what was it, 37 hours or 27 hours? Regardless, if you were to scale this up to the kind of resolutions that you were interested in, it would take a year or something.
Absolutely, no, I definitely see that. I mean, I'm just asking about the likely accuracy of a Gaussian approximation to the posterior, because you know, if your optimizer is returning you a Hessian matrix anyway, you know, you have a simple approximation to the posterior right there. The question is, how good is it? I mean, I like very much your hypothesis testing approach to the different kinds of uncertainties in the map. I think that stands on its own anyway. I just think it's interesting to know how the simple thing that I would think of doing compared.
Yeah, we haven't. My guess is that Gaussian approximation is not necessarily going to be that great, because specifically since we're using these basically L1 Laplacian type priors in some wavelet space, and in fact, actually a more kind of complicated dictionary of lots of different types of wavelets. So we're not, in a sense, kind of marginalizing over different types of wavelet representation. So I think because I think this is going to mean that it's less likely that we're going to have that the distributions are going to be well approximated by Gaussians, but we didn't explicitly check that, so we probably should.
Although the assumption of Gaussianity is also going to be quite scale dependent, right, in the weak landing setting. So for large scale structure, it's probably a much better assumption than for really small scale structure.
Yeah. The reason I was wondering about it was the issue of looking at marginal results versus conditional results. With the Laplace approximation, you could do either, whereas here you always have to be maximizing and looking at conditional slices. So I was just wondering about it in terms of getting a handle on whether that's important or not.
I mean, yeah. One thing is, if you do find that the Gaussian approximation to the posterior is good, I think that means that the marginal uncertainties are close to, if not exactly.
Exactly. Yeah, exactly.
But actually, I really don't think the Gaussian approximation is going to be good there, because really, you know, the prior is not at all Gaussian, right? The prior are these very sparsity promoting Laplace type priors.
Well, yeah, certainly I would expect the Laplace approximation to be better on the wavelet coefficients than on the map pixels.
But I mean, on the full recovered posterior, it's probably not going to be a great approximation. But indeed, it does give you more flexibility in terms of computing marginal uncertainties. Yeah.
But I guess to answer in summary, we know we didn't do that comparison. Sorry.
No,
Well,
no need to apologize. Anyone have any questions that aren't about marginal and conditional uncertainties? So just to give us a sense of the speed. I mean, if we're thinking of an LSST type data set, let's think about the full 18,000 square degrees where MCMC is not an option. Do you have a sense of how fast you could make a map out of that data set?
Okay, fine. So
maybe before you directly answer that, Matt,
okay.
I mean, why don't you talk about the extensions to the sphere that you're working on?
You first.
No, you go. But just discuss that as well.
Oh, okay. So, whilst this has been going through internal review, we've been extending this to the sphere. So that actually ends up being super simple, well, essentially, which is just replacing your wavelets with spherical wavelets and replacing your measurement operator with that harmonic space inversion rather than Fourier space inversion. So we have this running, so I can give you some ballpark estimates. So let's say a Euclid type reconstruction. The issue with that is it's large enough that you actually have to calculate, either do spherical corrections or just calculate it natively on the sphere. So I'm going to go with natively on the sphere. That then depends on what resolution you're wanting. So what kind of resolution would you be interested in? Angular, in terms of like an angular band limit?
I'd say arc minute.
Arc minute, okay, fine. So that's what an angular band 8,000. Yeah, so that's going to be quite slow. But I mean, it's doable. It's going to be certainly faster than MCMC, and we could we definitely could get it, right? You do these, right? It's just going to be a couple of weeks or something, right?
Yeah, you might need to run for a week or a few days on a supercomputer. But actually, we should also say that, so to go to what you'd ideally like to do, firstly, you want to go on the sphere, so that kind of slows you down. And of course, you have many more pixels, so that slows you down. We can probably just do that now, but it would take a bit of computer time, but it's certainly feasible. But actually, longer term, a big advantage of these convex optimization methods is that you can really highly distribute and parallelize them. So you can kind of break up some of these operators, and then you can spread both your computations and your data over different nodes. And in fact, I mean, the background is we've been working on similar types of techniques for radio interferometric imaging, and there we're trying to deal with the huge volumes of data we'll be getting from SKA. So even, I mean, at the moment we haven't done this in the cosmic share setting. Everything's just serial. But even with it being serial, I think we could probably push to full kind of LSST resolution on the full sphere now. But maybe we need to throw some compute power at it. But eventually, we could imagine doing this very quickly with a kind of distributed framework where, you can, for example, for radio interferometry, there were some things that were taking, maybe weeks to run, and then we could run them in about half an hour on a supercomputer. So I think the key point is that it's all feasible. For these large data sets.
For sure. Does that answer the question? Sorry.
No, it does. Great. It's great. Thank you. I mean, I think it's important to have a rough sense of these speeds, because you're inviting us to think about this hierarchical inference, which immediately makes us think. I mean, you heard Chris's question right at the beginning. He was asking about systematic errors, nuisance parameters, do more, with the mass map. And so we're always going to be demanding the fastest possible lower level inference in order to be able to explore hyperparameter space.
Sure. Okay.
Thank you. All right. So, and unless anyone else has a question for Matt, I think what we'll do is give ourselves 10 minutes of our day back. But before we all go, if you could turn your microphones off, we'll give Matt a round of applause for a very nice little talk. Thanks very much, Matt.
Yeah, thanks, Lee.
Thank you, Matt.
Okay, everyone. See you again next time. Thanks very much.
Thanks. Bye.
I think we need to stay on, right?
Bye-bye.
Okay.
Very interesting. Thank you.